discussing upon the application of the face field method for the fracture of thin-ply laminates. If someone cannot hear me because they tend to speak very fast and low, do let me know. That's it. Yes, I'm a student at the University of Porto, just informatically, and I'm supervised by Pedro Camanho, Albertino, Arteiro, and José from the University of Sevilla. So the main idea and the motivation for the work that I'm presenting is the difference that thin-ply laminates present in their damaged form compared to standard laminates. So Professor Pedro mentioned in his plenary talk all the different mechanisms you might see in standard composite. But in thin-ply laminates, those all seem to be suppressed, and you have an end-up form of fracture that lumps up into a single crack, essentially, so a single fracture plane. And this leads to the idea that you can use brittle fracture methods to simulate their damage in an equivalent single-layer form, so modeling the whole laminate at the macro scale to simulate its damage. And while you might have seen this quite a few times today, my notation is slightly different, so I'll just present it here. The main thing I point out is that, as everyone knows, the face field method relies on the minimization of the total potential energy. It has an elastic energy term and a fracture energy term, and the fracture energy term has a phase field in it, which goes into the crack surface density function to represent the crack in a diffuse form, going from 0 to 1 on damaged state. And to apply this to thin-ply laminates, the main thing you have to properly represent when going into a laminate at the macro scale is its anisotropic nature of its behavior. And one side of that is the elastic anisotropy that you have to consider. And thin-plies are kind of beneficial in that sense that compared to standard laminates, since they have a much thinner ply thickness, you stack within a certain thickness of a laminate, you can stack many more plies. So instead of 4 plies, you end up having 40 for the same thickness pretty much. So what happens is the bending extension coupling matrix for the composites people, so U tends to zero, and the extension null stiffness matrix tends to be equal to the bending stiffness matrix. So you don't have any warpage effects, and thus your laminate can represent by a single comply, so a one compliance and stiffness matrix, and that is what is done. And now the other thing you have to consider is also the fracture anisotropy, or I guess the anisotropic nature of the fracture energy. And that becomes a little more tedious because it is unknown what the fracture toughness is for laminates in different directions. But for the face field method, that's simple, I guess, or some people, smarter than me, have done this already. They figured out how you can represent the fracture toughness in different directions with a different value. And it's done simply by adding a structural tensor as the diffuse term of the surface density function. So that structural tensor is essentially a tensor that represents scaled preferred directions defined by vectors A1 and A2 here in bold. This is for an orthotropic material that are scaled by the scaling classes A1 and A2 respectively. And then you end up, if the math is done, you end up having a function for a function for the toughness of the function of the angle theta, which the angle theta is the angle the crack does with respect to the preferred direction A1. So if the preferred direction A1 is at 0 degrees, theta will then, and the crack moves at 45, theta will be 45. And you end up having this function, which can be plotted in the inverse form to give you the crack path, so the path that your crack will follow. And that is presented here in this very nice plot from Thin-ply, that you can see for a certain inverse toughness plot, if this CT specimen is loaded in tension, you can see that the path that the crack will follow, so the angle it will follow, is given by the point of the intersection, the tangential intersection with the line following the load path. And what is mainly of interest in this plot here is to show the influence of the scaling constants. So as the scaling constant changes its value, you get a different form of the inverse toughness, which essentially means you get a different toughness form. And if you know the crack path that you want to follow, so if you know that the crack wants to follow the preferred direction, it's simple to just add a very high value for the scaling constant. And this will essentially, your ellipse will turn into kind of a line, so you will always have the same value of the toughness, and your crack will follow the angle. But if you don't know that, so which happens in a multi-directional laminate, that I don't know where my crack will go if I pull the specimen, I have to properly represent the toughness for the whole laminate and then leave the model to predict its own way. And simply now I start to assume that my preferred direction aligns with the orthography accuracy, so my principal material direction. And I aim for 2 points in the inverse polar plot, so point 1 and 2 as I say here, which will give me the toughness for a crack moving at 0 degrees and the toughness for a crack moving at 90 degrees. And if I put them in the equation for the toughness, I can reverse engineer it to find the scaling constants that will properly represent the toughness of my laminate, at least in these 2 points. I'll keep that as a disclaimer. And I did point it out, in the isotropic phase of this small GC is introduced because instead of having now a single value for the toughness, since you have different values, it becomes a numerical parameter that I choose to represent the interlaminar toughness of a 0 degree ply. And that is because the analytical way to calculate, one of the analytical ways, actually the only one I know, to calculate the toughness of a multidirectional laminate has been given by Professor Camanyo and José Anatoli in one of their works. And they define the toughness, the interlaminar toughness of a laminate as the summation of scaled toughnesses of balanced sublaminates. So the laminate is assumed to contain balanced sublaminates, and they're scaled by the ratio of their thickness, and you can get the toughness of the laminate. And the method only requires the layup and the toughness of the 0 degree plies as an input, and then you can end up having your scaling constants as a function of only the layup and the toughness of the 0 degree laminate, of the 0 degree lamina. And for both directions, it's easy to calculate it. You just assume a rotation in your reference frame that you're applying the equations on. And in the rotated reference frame, you can get the other direction, assuming you do not violate the main constraint, which is that you have balance of laminates in your layout. And to verify this, what was done was some experimental results that were presented by Albertino for Thin-ply laminates and open hole tension were recreated. And the layup is seen here. It's a quasi-isotropic layup, so the toughness in the 2 directions does not have a difference, but it can still serve a purpose to validate the model, at least in the sense of using the layup and the toughness of the 0 degree plies as an input, and to predict the proper response. You can see here some details on the specimens. They were scale specimens, so it was a size effect experiment, and the discretization I used for informative reasons, and that's about it. And here you can see the results. So the process followed was the first experimental set, so one of the sizes was fit, so I obtained the optimal value of the length scale to use for my simulations. And then the other 2 sizes were predicted, and you can see here the force displacement result, the numerical one in red over the experimental one in blue, the phase field output, and the values of the predicted strengths, and the errors are in acceptable ranges. And the same was done for another set of experiments with Thin-ply laminates. This was a cross-ply layup. Again, you don't have a difference in the toughness in the 2 directions. But still, it was nice to see if the size effect can be captured, even in a different configuration, so it wasn't just the open hole tension. And again, size A was fit, and the other sizes were predicted. Very good errors here. So that gives some confidence in the method at least works in the principal directions, which is the main conclusion, I guess, and future work, is what I'm going to try to do is make sure that in between the 2 anchor points that I mentioned, I'm representing the toughness of the laminate correctly, so I can extend the method to multi-axial loading or off-axis cases, in cases where you would have shear or anything else where you would not know how to predict the crack path, because here the expected crack path was actually following the x-axis of the tension. That's it.
Yeah, thanks, Anatoli. So, yeah, other questions? Yeah, there's one question.
So, you said that the formulation is good for balanced laminates, right?
Yes.
So it's like 0 plus minus 45%. Well,
it needs to contain, so the layout needs to contain balance of laminates. So it could be 0 plus minus 30, plus minus 50, plus minus 25. It just has to have a plus minus of any angle other than 0 or 90, because that's the analytical equation that exists at the moment.
Okay, yeah.
an extension to the analytical equation would happen, so you could have any layout, but that will mainly be the issue in the off-axis angles where I don't have an exact analytical way to calculate the toughness and I have to go via numerical or some other method, because there I don't have balance of laminates. If I cut a 090 cross ply in 20 degrees, I will not have balance of laminates in it. The
Okay.
layout will not see balance of laminates, if it makes sense.
Thank you.
Yeah, maybe one rather technical question. I mean, it means you have a layer of elements, right? And every single layer has different local orientations.
No, sorry. That wasn't clear.
That
No.
was okay.
So I have just one plate. If you can imagine, so I have a 2D model that I'm running here.
Okay.
But you can imagine it's just one plate, represented by the equivalent stiffness of the laminate.
I see.
And then for the orientation, it's just a matter of
Yeah.
putting an orientation, a local orientation in Abaco. So
Okay.
I assign orientation to the material. So here where I use the principal axes, it's just XY.
Mhm.
And those are my principal axes, and everything else runs internally in the equation.
Okay, I see.
So the laminate is represented just with one layer. It's represented by the equivalent stiffness
Mhm.
and the equivalent toughness based on the equations from Reinoso.
Okay, I see.
So that's the idea that we want to try to follow in kind of the on-axis cases
Mhm.
that we should know.
Are there some more questions? No, that's not the case. Then thanks again. Julie.